Okay, to review and to summarize the thing that we have discussed regarding the performance equation for a batch system. So for epsilon A equal to 0, this means that your system is constant density system. And these constant density systems are most of the time liquid phase reaction. I have mentioned already that this will be the suggested formula for the performance equation for your batch reactor. Now for gaseous reactions, still on the batch reactor, then we have to use the other formula, and that would account already the linear variability of the volume. So the volume now was changed to V sub O times the quantity 1 plus epsilon A XA. And as such, if you notice, the VO here was the constant that was divided to the, or that was used as a divisor for NaO, making it CaO. And the thing that remains after your integral sign is your differential for XA, the rate, which is also dependent on conversion, and this quantity 1 plus epsilon AXA. So you have two sets of formula for batch systems, one for liquid phase reactions, constant density system, or for gaseous reactions, in which there is variability in the volume. So this is your performance equation for a batch reactor. Now let's move on. Now, when we speak of steady state reactors, I'm referring to the constantly stirred tank reactor and the plug flow reactor. There is this added uh, concept or characteristic that could only be associated to the two, or oftenly associated to these steady state reactors. We have the case of the space-time and the space velocity. So the space-time is the time required to process one reactor volume of feed measured at specified condition. Or simply put, how long will you be able to process one reactor volume with this particular degree of conversion? And that would be the space-time. And since it's asking for how long, it has something to do with time, the unit is time. So, but take note the time it would take to process one reactor volume of feed at specified condition. The opposite of the space-time is the space velocity, or rather the reciprocal. That's the appropriate term. The reciprocal of the space-time is the space velocity. It's 1 over tau, and this is, take note, the number of reactor volumes of feed at specified conditions which can be treated in a unit time. For example, your answer when you computed for the S is 1.5 per second, example only, or 1.5 per hour. That tells you that your reactor can process 1.5 volume of feed for every hour in that particular type of reactor. So the unit is per unit time, telling you the number of reactor volumes that could be processed per unit time that was used as the unit as indicated. Okay, so space-time and space velocity. Now, the space-time could be expressed in terms of this formula for our, both for our steady state reactors, CaO times V over FaO. CaO is the initial concentration, volume is the volume of the reactor, and FaO is the molar feed rate. The molar feed rate. So molar meaning it could be mole per cubic meter or pound mole per cubic feet. Ano, mole per hour or mole per second. Molar feed rate, or English, if it's English, it's pound mole per hour, something like that. So that's your FaO. Now, if you have the volume and the concentration, the remaining unit is mole. This one is mole per unit time, so the remaining unit uncancelled is time for the tau, which is rightly so, should have a unit of time. So this is the space-time for the two steady state reactors. Now, so we go to our CSTR. So you could see here in the CSTR that you have FaO, the initial molar feed rate, and F is of course the feed rate after the reaction has already proceeded inside your reactor. So this is for your CSTR. Now, in the case of our material balance equation, if you recall, it's in is equal to out, accumulation, and disappearance due to reaction. So the in is equated to the sum of the out, accumulated amount, and the disappearance due to reaction. In the case of the steady state flow reactors, there's two of them, the CSTR and the PFR, there's no accumulated amount. Why? It's a no-no that your reactor should overflow or go dry. So meaning the volume inside your reactor at any time should be a constant. So in that case, there is no accumulation. Now, it's the same thing with CSTR and PFR. So, no accumulation terms. So, the remaining terms in your material balance or in your mass balance equation would be in is equal to out plus disappearance due to reaction. There is no accumulation. Okay, so this is the thing that you have here. The assumed rate of flow in is equal to the rate of flow out. So since the two are equal, then they will just cancel each other. Now, Fa, the molar rate in which your reacted mixture leaves your reactor is equal to V sub O Ca. Now this one class, this is small v. This is not to be misunderstood as capital letter V sub O. So again, your capital V sub O is initial volume. When you speak of steady state reactors, the small v sub O is volumetric flow rate. This one, so let me annotate. This one is volumetric flow rate. It's not initial volume. Okay, so the volumetric flow rate times the concentration of the remaining A unreacted would give you a unit which is in pound mole per unit time. Now, this is the initial molar feed rate. The volumetric flow rate also times the initial concentration. So you can see here V sub O is the volumetric flow rate, which will have a unit of volume per unit time. So noting that there won't be any accumulation, then you have here the corresponding performance equation for a CSTR. So let me just erase. Okay, your input would be this. Your output would be this. Disappearance due to reaction would be this. And the three will be the three will be seen in your material balance equation. So your in is equal to out plus the disappearance due to the reaction. Disappearance due to reaction. Now, you could see that here FAO here, that's FAO in, and your output is FAO1 minus XA. There's something new here. This is your this is in, this is out, and this is disappearance due to reaction. So I will just write due to reaction. Okay. Now, we can rearrange terms here. Before that, however, we need to cancel this one. If this is expanded, the FAO here and the FAO here will cancel, leaving you with 0 is equal to FAO XA, which is negative, here negative, minus rate B. Actually, it's not minus, but since this is written as negative, so it's written as negative there. If you are to transfer this negative FAO XA, so this would be negative, or rather no, it's not negative anymore. Let me erase. This is negative, so when you transfer, that will become positive already. And what you have here on the right side is the rate times the V. This is one entity. So para hindi ma-confuse, it should be written as plus the product of negative R sub A V. Okay, so this is it. Now what have you seen here is that there was a splitting here of the term. So you keep the V here, and the V and the FAO went together. So you transfer the FAO here, and the rate transferred in here. This is the resulting equation. Okay, V divided by FAO, XA divided by the rate. This is the resulting equation. Using the definition of space-time and space velocity, you can change the, or you can represent the tau, which is V over VO, which is actually 1 over S, the reciprocal of the space time, which is now the space velocity. You have this one. Now, how could it be missed? How did this one came about? Anybody? You have the tau, which is equal to V over VO. This is new, right? Because the formula that you saw here, I will erase, I will clear first. I'll show to you the formula that was, this is your tau. This tau, I will annotate, can also be solved using pure dimensional analysis. It could be the volume of the reactor divided by the volumetric flow rate. Volume over volumetric flow rate would still give you a unit in time, right? So you have two formulas, this one and this one for the tau. Okay, the view. Now let's go back to our slide so you can answer the question that I just posted. Okay, this one, let me just erase. Okay, it can stay there. How did this one came about? I would like to ask somebody, or I give you a few minutes. How did this particular tau being equal also to V over V sub O, small v sub O, equal to CAO XA over the rate? Can you check? Or if you have a piece of paper there, can you check how did this particular formula came about? Because what is so likable about the CSTR is that you don't need to integrate. This is in itself its performance equation. That is the performance equation for your CSTR. Now, this is an added formula for you, but this one is derived from the relationship that you have here. So anybody who can tell me how did this particular formula came about? The tau is equal to CAO XA over the rate. The things that you will be needing in derivation are all in front of you, plus this one. This is your tau. How did this one came about? Anyone? Who can dictate to me what happened here? I don't want to leave the slide so that everything you could see, or the things that you will be needing, you could see. Anyone who know how this one came about, or how do we rewrite it? Or anyone who just can dictate to me? I only have 13 students now. What happened to the rest? Anyone? Okay, this is it. Okay. Now we will use the performance equation that we have here. That way we can arrive at the new formula that we have for the space-time for your CSTR. From that particular formula that you have there, you have V. I'd like to change the FAO. You see this one, the V sub O CAO. Excuse me. And you have XA over the rate. I think it's very easy. Now, if I will transfer this one here, you will have, I'll write here, V over B sub O, that's small b sub O, equal to CAO XA over the rate. The V over BO, as stated in the previous slide, is tau. So tau is equal to CAO XA over the rate. There is no need for you, again, to integrate in the case of the CSTR. So that is why my students will always be very happy, especially if they are solving a CSTR problem, a single CSTR problem. Why? Because there's no need for them to deal with the differential equation. If you are asked for the time to process a particular reactor volume based on conversion, this is the formula. But if you want a generic formula where you can derive the rest of the requirements in the problem for a CSTR, that formula would be this. This is the performance equation for a CSTR. Any question? So no more question. I will just clear the markings here. Okay, we'll proceed. So that's for the CSTR. Now, again, there will be an algebraic relation in terms of concentration and the rate law for each specific case. So this is now the formula that we had written on in the previous slide. For a well mixed reactor, your concentration is the same at all points in the reactor, and it's also equal to the outlet concentration. Like saying that the concentration here at any time is also equal to the concentration of the thing that leaves the reactor. So anywhere here, you have the same concentration at time t with that of the effluent or the outlet concentration. So that's in the case of your CSTR. Now, the last performance equation is, before we go to that, we have here the comparison of the performance equation of the first two reactors so far that we have discussed. This one is for the batch, and this one is for the batch liquid phase, if you recall, and this one is for the CSTR. Okay? No integration. Here we need to integrate. Now we go to the PFR. So you have an industrial PFR here in the picture. And let's say we will consider this very simple tube or cylinder as your plug flow reactor. So you have the molar feed rate entering this particular point in your PFR, and F is the molar feed rate after the reaction has already proceeded. Now, the elemental volume that was considered in this reactor will be this portion here. So it's like we cut a cylinder here. And that's where we're going to perform our material balance. So this is the differential volume or the elemental volume in which we're going to perform our material balance. So this is the delta V. We have V entering this section, and the volume that leaves this section is, of course, the V plus the delta V. This V plus the delta V will be the volume leaving this elemental volume. Okay? So this is for our plug flow reactor. Now we will derive its performance equation just like the way we did with our two ideal reactors. Okay, so this is it. Now you have no accumulation here. So there's no accumulation in the case of the PFR. And you only need to consider two terms on the right. You have the uh, outlet rate and the disappearance due to reaction. That's what should be appearing on the right side. And you have here your left side input. Now you have this. I'd like to rewrite this initially as you have here dV being equal to FAO dxa over the rate. That's the simple uh, integrals that we will be having, that we will be considering in the case of the plug flow reactor. Okay, no accumulation also. The resulting terms will be this one. Now, look at it intently. So you have dV and you have FAO, and then you have this integral here, dxa and the rate. Now, what happened is we place the FAO here. So you have the integration of the volume, the change in the volume from 0 to V. So now it would be V over FAO. This V over FAO is tau over CAO, primarily because this V and this is VOCAO. So this would be V over CAO. This is your tau over CAO. This one is your tau over CAO. So that's the reason why you get to see here. On the right side, you see it's left because you can place any rate law here based on what is stated in the problem, or based on what you have determined if you were asked to first determine the appropriate rate law. So this one changes depending on the appropriate rate law that will be used in the problem. So that is why you have only here rate. And then you have here the differential of XA. So notice that we don't, unlike the CSTR, that we did not have any integration. In the case of PFR, you have integration in here. So tau over CAO or V over FAO, this is how it should be interpreted, is equated to this integral on the right side for your PFR. Again, V over FAO, if this is the one that is given in the problem, or tau over CAO, is to be equated to what is written here on the right side for your PFR. Okay, we'll proceed with the next slide. This is for your PFR. And that's it. So for your performance equation for the PFR, because that one is already a sample problem, this will be your performance equation, this entire thing. So we cannot simplify it here for now because we have integrals to deal with, okay, in the case of the PFR. If we don't have volume variability in our PFR, the performance equation of a PFR and a batch reactor is just the same if we don't have any variability in the volume. Okay? The performance equation of the batch reactor and the PFR are just the same. Now, so let's go to this sample problem. Okay, sample problem number 1. Now, this one is talking about a CSTR. Okay, let me just get my cell phone. Okay. 1 liter per minute of liquid containing A and B. So initial concentration for A is 0.10 mole per liter and B is 0.01 mole per liter flow into a mixed reactor of volume equal to 1 liter. Now, the materials react in a complex manner for which the stoichiometry is unknown. So we do not know the stoichiometry of the material. The outlet stream from the reactor contains A, B, and C in the following concentration. So you have CAF, this is the final concentration of A remaining is 0.02 mole per liter. CBF is 0.03 mole per liter, and CCF being equal to 0.04 mole per liter, and it's shown here in the figure. Find the rate of reaction of A, B, and C for the conditions that are stated in this particular problem. So you have this particular information for us to be able to process this problem without having to go back to this slide. Let me take a picture of this. Okay, so we go to our board. Number 1. There's a need for us to write down the given information. That way we will not have to go back to the slide that for needed information that we might use along the way as we solve. So we will get the information based on the illustration. So I'll write the illustration here. You can also get a piece of paper there and copy the process of finding the solution. That way you retain something, and then when you, by the time that you study on your own, you have retained already something. It's not so hard to recall. So 1 liter per minute of liquid containing A and B. So you have 1 liter. So this volume is 1 liter. Now the initial concentration is 0.10 mole per liter. And for B, 0.01 mole per liter. Okay? The volume of this mixed flow reactor is also 1 liter. Materials react in a complex manner in which the stoichiometry is unknown. So we don't have a chemical reaction. Now, the outlet stream of the reactor contains the following. So this is already final concentration, 0.02, 0.03, 0.04. Okay. By the way, in the first statement, it says 1 liter per minute. So I'd like to erase this one. It's not volume because it's volumetric flow rate. So you have here V sub O is 1 liter per minute. Okay. Now you are asked to determine the rate of reaction. The rate of reaction of A, B, and C. So it's asking for you not the rate equation, but rather the rate of reaction, meaning it's asking for the actual value, meaning it has to be numeric. So the rate we do not know the identity of, by the way, you see already A and B here. It's in the initial stream that entered your CSTR with a volumetric flow rate of 1 liter per minute. So meaning these two, it's just okay to assume, oh, maybe these two are reacting species. So I write here negatives, okay? Because we're not provided with the chemical reaction, so there's no way we can tell which of the A, B, and C that was stated here is reactant and which one is the product. In this case, since I already saw here an A and a B, though it's not still correct to say now 100% sure that they are reacting species, I'd like to assume that they are the reacting species. Now, since I have already assumed that A and B are the reacting species, then the C must be the product. Again, I'm using class the term react, assume. So I'm assuming. I'm not sure whether B is the only species that is reacting, forming product A and C, or it could be A reacting, forming product B and C. I am assuming because I don't have the chemical reaction. And I hope you are understanding why I'm saying I am only assuming. Okay? So I have assumed that A and B are reacting species, and your C is your product. I have a C here. Okay? Now, what do we do next? Remember, remember that of the three ideal reactors, only the CSTR does not need us to integrate. And it has a very simple performance equation. What is the performance equation of the CSTR? If you have written it a while ago, can somebody dictate to me the performance equation of the CSTR? What was the performance equation of the CSTR? By any chance? Somebody copying it? So we have tau is equal to CaOXA over the rate. Right? Is this the performance equation of the CSTR? Just give
Yes,
me,
miss.
thank you, salamat. May upod ko, kala ko ako na lang ditawo. Okay, so this is the performance equation of the CSTR. Now I need to find the rate in terms of A. So this must be my equation to use, right? Now, this tau, I can change that to V over V sub O. You may ask, Miss, why are you changing it to V over V sub O? Because I see a V here and a V sub O here. So I'll place here equal to. Now, based on our basic fundamental discussion on kinetics of homogeneous reaction, what is CaOXA? Excuse me. CaOXA represents the what?
Ca.
CaOXA represents the, what does it represent? So you're going to answer me a phrase. You're going to answer me a phrase or a relationship. CaOXA represents the what?
Reacted.
Reacted. Thank you. Very good. The reacted amount of A. Now, based on what you're provided here, look at it intently. What is the reacted amount of A? And based on what you have learned with kinetics of homogeneous reactions, what is the reacted amount of A?
Point 10 minus 0.02, miss.
Ay, thank you. Very good. Ang reacted amount of A is ang initial amount minus the final amount. What you have initially minus what you have left is the amount that has reacted, right? So we place here, rate. So see, the problem that we have regarding rate is now solved. I'll place it here, then I'll have this one here in the denominator of CaO minus CaF. So I will place now 0.10 minus, I can't write, 0.02 divided by the volume, which is 1 divided by 1. 1 liter divided by 1 liter per minute. This one is mole per liter. So your rate is 0.08, right? Mole
Yes.
per liter per minute. Okay? Now you use the same principle. You use the same uh, analogy with the B and the C. So I'd like to write here. So this is already your answer. So rate is equal to 0.08 mole per liter per minute. So this is one answer. Okay. Now we go to B. The same. We assume that B is a reacting species, so I will have here the rate in terms of B. This time I will place here CBO XB. And in here, I will still have the V over V sub O. Your CBO XB is CBO minus CB divided by V over V sub O. Now, let's check. CBO is 0.01, CBF is 0.03. 0.01, 0.03. 0.01 minus 0.03 divided by 1 over 1. Now, what is it that you have observed? This is negative, right? 0.02 mole per liter per minute. Negative. Then our assumption that since B is initially present in the reacting mixture, that it is a reacting species is wrong. It doesn't mean that when you see a species being mixed with another, it's already a reacting species, meaning it's needed in the reaction to produce the product. B in this case is a product of reaction, or shall I say one of the products of reaction. So I will write, therefore, B is a product of the reaction. And the rate, see, I'm used to writing negative, and the rate will be now positive, should be written as positive. So the rate of formation of B is 0.02 mole per liter per minute. So that's your B. Okay? Now, any question? None? Here we go. So C. So we assume C is product. We don't see any C initially present. So it must be product. So I place here R sub C is equal to C CCO XC divided by V over VO. Now, since we assume that R sub C is a product, what is this C sub C XC? What does C sub C O XC represent? If C is a product based on our assumption, it represents the what? The, anyone?
Ang nagkaka-form, miss.
Ang nagaka-form. Very good. Ang nagaka-form. So if it's nagaka-form, then you will have a different formula here in the numerator. Ang nagaka-form will be the CCF minus the CCO. The final amount minus the initial amount is the amount that was formed due to the reaction. Okay, so hindi siya parehos ang previous sa tunga duha formula. But still you have the V over VO here. So final C sub C is 0.04. So this is 0.04. There's none initially present, and we have 1 over 1. Then we are correct in our assumption that C is really the product. So this is mole per liter per minute. So as to the requirement in the problem, as to rates of reaction of A, B, and C, this will be your answers. So R sub A will be 0.08, R sub B will be 0.02, and R sub C would be 0.04. Now, since you have already, based on this particular performance equation of the CSTR, you already know which is the reactant and which are the products, we can now write this as A forming B plus C, right? The B should be written on the product side because it's a product. Now, I'd like to use a different font. This is not being asked in the problem, but I will just ask it just the same. I'll write here an X, I'll write here a Y, and a Z. The reason why I'm writing here an X and a Y and a Z is I want you, though it's not being asked in the problem, I want you to give me the stoichiometric equation or the chemical reaction for this problem based on the values that you have solved. How will you find X, Y, and Z? That way, this time, even if it's not in the problem, you know how to come up with the stoichiometric equation or the chemical reaction based on the values that you were able to arrive at or calculate using the performance equation of the CSTR. How will you write or how will you calculate X, Y, and Z? Any suggestion? You have learned it in kinetics of homogeneous reactions, fundamental principle in kinetics. What would you do?
I-equate sa tatlo, miss.
Oh, very good. I-equate sila tatlo. Very good si Sokto. Okay, so i-equate sila nga tatlo. So you have here rate over X, rate over Y, and rate over Z. Okay, now I will use the values that we got. So we'll have A is 0.08 and B is 0.02, 0.04. So this is 0.08 X Why did I not erase everything? 0.02 Y and you have 0.04 Z. Now, tell me what's the next thing that I should do? Suggestion? Suggestion. No suggestion? There. We let Y equal to 1. So if you let Y equal to 1, you will have 0.08 over X is equal to 0.02 over 1. Telling you that X is equal to?
4.
Correct. Now, same thing. So, nini naman ang duha. So, you have 0.02 is equal to 0.04 over Z. So, Z is equal to 2, right? Now, let's check whether we will have a, shall I say, a plausible, acceptable initial assumption based on the stoichiometric equation that we will be getting. So I will write now 4A forming B plus 2C. Right? Now check whether it would it be right if I will have these two? We will check. You can check whether this is already okay by using these two. Okay? Checking. I'll write here checking so that we're on the same slide. You'll have 0.08 divided by 4. Is it equal to 0.04 divided by Z. 2. This is 0.02. This is 0.02. So check. So this is the stoichiometric equation. This, they should be all equal no matter what the pairing should be. So then this is your stoichiometric equation based on the data that we processed using the performance equation. So in this case, we arrive at the stoichiometric equation using the calculated rates from the performance equation for our CSTR. This is not us in the problem, but just the same, I'm placing it here so you will have an idea on how you will find the stoichiometric equation given the rates for a CSTR. Okay? Any question? Okay, so if there are no more questions, I'll go back to the slide. So this is our slide. And these are the very important points that I have summarized regarding the first example. So example 1 demonstrates that we can observe the reaction rate in a mixed flow reactor by observing the steady state concentrations going in and out of the reactor. So telling you, you can solve, simply put, you can solve for the rate of reaction, meaning the quantity that is using the values of the concentrations living in the reactor or is entering the reactor. Second, we do not even have to use stoichiometry for observing this, but in the end, the stoichiometry can also be deduced out of the values that we have taken. Or simply put, hindi tagani kinanlan ang stoichiometry, kaya ang stoichiometry ginkuha ta pa halin sa values nga na-solve naton. And last, observing the reaction rate does not mean, this is very important, and though this was asked already, we obtain a reaction rate expression or a reaction mechanism. When a problem is asking you for the reaction rate, it is a value, a quantity, not an equation, not a mechanism. Okay, so this is for the first sample problem for this set of slide. Now, I don't want you to burden yourself in this wellness days week. So we will end here. But the rest of the slides for reactors, ideal reactors, was already uploaded in Canvas. So feel free to scan through the slide. And if you feel like studying or reading, you may study ahead. But we will continue on this next week. Any question? I will stop sharing now. Do you have any questions?